Welcome back to the geological and hydrogeological parameters and conditions for groundwater heat exchangers. We stopped at the hydraulic gradient. This is another important hydrogeological parameter that depends on the water level. It equals the ratio of the difference in elevation of the groundwater table at 2 points compared to the horizontal distance between those 2 points. The hydraulic gradient can therefore be determined directly from the groundwater level maps. And in many aquifers, there is a gradient in the groundwater table, meaning that groundwater flows from higher to lower elevation, perpendicular to the groundwater contour lines that you see here on this map. A groundwater with a very, very low gradient and therefore without or with only very little flow movement can also occur in some areas. And as you can imagine, this would be good for aquifer thermal energy storage, whereas faster flowing groundwater is more suitable for the groundwater heat exchanger of the pump and dump system. The connection between the hydraulic conductivity and the hydraulic gradient is described in Darcy's law, which is only valid for the porous aquifers because here we have this laminar flow. The flow rate equals then the hydraulic conductivity times the gradient times the cross-sectional area where the groundwater flows through. And the flow rate divided by this cross-sectional area equals the Darcy velocity. This means actually that changes of the hydraulic permeability inside the aquifer result into changes of the hydraulic gradient. So imagine the groundwater flows in a highly permeable gravel and suddenly hits a sand pocket. Now the same amount of water has to flow through the same cross-sectional area, but with less pore space, hence a lower hydraulic conductivity. What happens? The hydraulic gradient increases, the water level gets steeper to keep the groundwater flow velocity steady. Now we come to the last hydrogeological property presented here, which is the groundwater temperature. The groundwater temperature is impacted by solar radiation and subordinately infiltration water. The influence of daily atmospheric temperature fluctuations on the groundwater body is insignificant due to its penetration depth of only a few decimeters. However, the situation is different for seasonal temperature fluctuations, whose influence reaches deeper into the subsurface and thus affects the temperature of the groundwater. The annual atmospheric temperature curve for Central Europe can be well described by a sinusoidal curve. And this sinusoidal curve is dampened in the subsurface, as you can see it in this graph here, until a certain depth, the neutral zone, then there is no longer any fluctuation and we have a stable groundwater temperature throughout the year. And from this depth, an annual mean temperature prevails, and this is then very dependent on the atmospheric annual mean temperature. Below the neutral zone, the temperature is influenced by the geothermal gradient. Here, the temperature increases accordingly to the geothermal heat flux. So anthropogenic heat sources, which cause the so-called urban heat island effect, also have a significant influence on the groundwater temperature in the urban areas. If you live in a larger city, you are probably aware of this effect, particularly in summer. Cooling effects such as vegetation are less prevalent and the temperature in the cities is warmer than in the surrounding rural areas. However, this warming does not only occur on the surface, it also migrates into the underground. And in the underground, we have additional heat sources like tunnels, sewage and district heating pipes, garages, and cellars. And these underground installations are largely sources of heat and contribute to an increase in the temperature underground. However, there is one installation that can also contribute to a reduction of this urban heat island effect. Guess which one? You are correct. Geothermal heat pumps in heating mode because they cool the surrounding underground. Now, you might ask, is it a problem that the underground gets warmer and warmer? Well, on one side, it's great if you still want to use it for heating. On the other side, the cooling potential might be decreasing. Free cooling, the cheapest way of cooling because it doesn't need a heat pump, is only possible at underground temperatures of around 20 degrees Celsius. So the change of groundwater temperature can already be seen as a risk. Now let's see what other risks and limitations there are in the context of groundwater heat exchangers in the next part.